Okay, welcome back to the C++ course. This is chapter 17 called the Standard Template Library. Finally, we get to discuss this topic in some amount of detail. I've been referring to it throughout the entire course here, so we're going to take a look at kind of in general what is the STL. We'll take a look at two types of things you find in the STL, namely containers and iterator functions. We'll take a look at the vector class, which we've already seen plenty of examples of, but it definitely is part of the STL. We'll take a look at some other parts, some other specific implementations in the STL, things like map, multi-map, unordered map, and then correspondingly set, multi-set, and unordered set. There's a bunch of algorithms we get kind of out of the box with the STL, so we'll check those out. And something that sounds impressive, if you're out and about with your friends, introduction to function objects and lambda expressions. Okay, so what is the STL? It is a library containing templates. Okay, keyword templates. Remember from a lesson or two ago we talked about templates. That is the T of the STL. So we're going to be making heavy use of the C++ idea of templates. A library containing templates for frequently used data structures and algorithms. It's kind of like a bunch of pre-built stuff that we can use in our programs so that we don't have to basically reinvent it from scratch. Now, C++ calls this the STL. Other languages have similar packages and ideas called something else. But just know that most languages support something like this. An example is the vector class, which we saw in chapter 8. It is a data type defined in the standard template library. So a little bit about containers and iterators. So two important types of data structures in the STL. One is containers, so classes that store collections of data and impose some kind of restriction or organization on it. So basically different ways of structuring your data structures, like a vector. Other examples are stacks, queues, sets, and maps. These things impose some sort of organization in the way you're able to store data within them. I guess an array is kind of along the same lines, but an array isn't necessarily, like, the way we've been using arrays isn't necessarily part of the STL. There is an array component of the STL, but what we've been doing with them really isn't that. And then an iterator, like a pointer, provides mechanisms for accessing elements in a container. So you've got all your data structured inside a container. Now you can use iterators to kind of navigate through those containers and get at different pieces of data within them. So we have two types of containers in the STL. We have sequential containers, which organize and access data sequentially, much like an array. These include the array, the vector, something called a DQ, and a list container. All of these are ways to store data, but again, they have different rules imposed on them, and as far as how you're able to use them and access that data. Values are stored by a position, like an index, in a sequential container. Okay, hands-on, page 1036. There are lots of hands-ons in this chapter. It's probably going to be a longer one, so we'll try to keep it at 2 hours or less if we can at all help it. So yeah, let's check out this table. So an array, here's just some sequential container examples and descriptions. So like an array is a fixed size container, similar to an array. A DQ is a double-ended queue. Probably don't know what a queue is at this point, but it's like a vector, but designed so that values can be quickly added to or removed from both ends of basically the list. Forward list is a singly linked list of data elements inserted or removed from any position. A regular list is like a doubly linked list of data elements, values inserted or removed from any position. And notice how we will be discussing a lot of these data structures in some future chapters. And then the good old vector works like an expandable array, which we know about. So then we have associative containers, use keys to store and to allow data elements to be quickly accessed. These things are like the set, the multi-set, the map, and the multi-map. Containers and their unordered equivalents. So you can keep ordered versions of these and unordered versions of them. So the key of an associative array container plays the role of an index in a sequence container. And I'm hoping there'll be an example here coming up soon. Most of us are pretty comfortable with the sequential containers, but the associative containers may be fairly new to some people. Here's some examples, I guess, like the set. So a set stores values that are sorted in some order with no duplicates allowed. So notice here are some of the rules imposed on these data structures, like with a set, cannot have duplicates. A multiset, same as a set, only duplicates are allowed. So then a map maps a set of keys to data. The keys are kept sorted in some order, and duplicate keys are not allowed. Then you can see the rest. With a map is sort of like, you know how in an array you would say, give me index 2, and then you would see what's stored at index 2. With a map, it's sort of like, give me index, let's use a dictionary as an example. Say we're storing a dictionary in a map. Say, give me word programming. And then what is returned to us will be the definition of that word programming. So it's like you give it a key, you give the map a key, and then it gives you back the value. It's like key value pairs almost. Again, I give it a word, it gives me back the definition. In an array, I give it an index, it gives me back what's stored at that location. Okay, container adapter classes implement rules for how its values are stored and retrieved. These are not containers in themselves, but they're classes that use containers in the underlying implementation. So things like a stack, a queue, and a priority queue, again discussed a little bit later in chapter 19. Here's some examples. So a stack, stacks and queues. If you're familiar with these terms, just kind of colloquially in like just the regular language, English language, a stack is like a last in, first out container where you retrieve an element from a stack. The stack always gives you the last element that was inserted. A queue is like a FIFO or a first in, first out. When you retrieve an element from the queue always gives you the first or earliest element that was inserted. Priority queue is a modification of this, stores elements in a vector where each stored value is assigned a priority, and the element that you retrieve always is the element with the greatest priority. So then part of the priority queue is then making sure that you kind of have this notion implemented of what is the highest priority thing in the priority queue. So a queue is like a line. If you're waiting in line for like a roller coaster at an amusement park, think of a queue. A stack, to use an American example, is sort of like a stack of plates at a buffet. So you take the top plate off of the stack. When the worker reloads the stack of plates, they put a stack down on top and push all the other plates down low. At least that's how I think of it. Okay, so a word about header files. So programs must include specific files in order to use these containers. Things like the array, the DQ, the list, stack, vector are also the name of the container. Other files have multiple containers. Map has map and multimap, and then queue has queue and PQ, or priority queue, as they're sometimes called. Taking a look at the array class. So this is, again, like not just general arrays that we've been using since almost chapter 1, but the array class. So it's introduced in C++11. It really beefs up what we can do with arrays, builds some functionality around them, makes them nicer to work with. Okay, we know this is hopefully a review. Arrays are a fixed size. All elements are of the same data type. Provide a data type and a size on the declaration. So if we wanted to create a new array, sort of like how we create a new vector, when we create a new array, we have to say what type of data are we storing in the array, and then the size of the array, and then the name of it, like this. We can also provide it as an initialization list. So we say this is an int array of size 3 called primes, and then we initialize it with those 3 values here. So the biggest thing to get comfortable with here, I guess, is probably the angle bracket notation. Generally speaking, I always tell my students this: when you see angle brackets in C++, usually what you're going to see inside of them is some kind of data type. Just like with a vector, we say we store a vector of ints or chars. Here we're creating an array of type int of size 20. The array class overloads square bracket to allow access to elements using an index, but it does not perform bounds checking. This is C++ after all. We have to make sure we're doing our own bounds checking, making sure that we're not accessing an element outside of the bounds of the array. We do get access to the size member function, which returns the declared size. So in the previous example, we can say my primes array divided by size, whatever they're doing here. So we can say, it's supposed to be dot size? That's what I would say. Yeah, primes dot size. So it gives me the size of my primes array. Keeps us from having to, like with the regular old C++ arrays, we had to kind of keep track of the size manually. With the size, or with the array class, we're kind of given that functionality out of the box. One of the many benefits of using the STL. Some more member functions. So member functions provide capabilities beyond ordinary arrays. Things like we can test to see if the array is empty, give me the size, give me the front element of the array, give me the back, give me at index. We can traverse it, we can reverse traverse it, etc. All right, maybe this will be a real hands-on 1038. Yes, indeed. Okay. I've got my solution created, example 17-1. Include string. Just a little practice here with the array portion of the STL. Const int size equals 4. Here's the new bit of syntax. So we're going to create an array of strings of size called names and initialize it to something. Oops. Like so. Semicolon. We already have a problem. So array, string. Oh, we need standard namespace and null as well. Okay, cool. So I got my array of strings. I can just for over it, for loop it, int I equals 0. I is less than names dot size. Don't forget the open closing paren, I plus plus, and then cout names at I endl. No big deal. Just more or less a little warm-up exercise here. There's my names. Kevy. All right. Here's this big warning. The array class's square bracket does not perform bounds checking. As with regular arrays, you must be careful not to use an index that's out of bounds. All right. Here's another table. Let's check it out. Yeah, so this is just a bunch of array member functions, a nice little sort of index of what types of things you can do with the array class. Here's a swap function. Second argument must be an array object of the same size and type as the calling object. The function swaps the contents of the calling object and the second object. You can swap array contents. Nifty. Okay then, iterators. So iterators, when you think iterator, think pointers. They're a generalization of pointers. They're used to access information in containers, and there's many types of iterators. So you can have a forward iterator, which would use the ++ syntax, bidirectional, ++ minus minus. You can have random access. You can have input iterators used with cin and istream. You can have output iterators with cout and ostream. How do you define an iterator? It's rather nasty. I've never liked this syntax much, but each container class defines an iterator type used to access its contents. The type of an iterator is determined by the type of the container. So this is how you would define an iterator for our array. So keyword array, type of the array, : iterator, space, name of the iterator. Here we have the same thing, same kind of thing. only iterator is called y. So x is an iterator for a container of type array of type int. So that's going to allow us to kind of loop through or iterate through our int array. Cool. Each container class defines functions that returns iterators. So if you say begin, that would point the item at the start of the container. End points to the location just past the end of the container. So if we have an int array created like this, we can create an iterator for that array like this. So same syntax, same type, keyword iterator. Then the name of it, aint, equals our int array dot begin. And that's going to cause aint to point to the item at the start of the container. Let's check out a hands-on. (17-2). Include string, include array, standard namespace. Let's see what we're doing here. Yeah, we're going to create our first iterator. Whenever we're doing something for the first time, it's always good to actually type it out. And const int size equals 3. Now we will create the array of type string of size, names equals Bill, Bob, Joe. I'm so creative. Okay, now we're going to create our iterator. So array, same type, string, same size, colon, iterator, keyword, it. Common name for iterator is it, or prefixing with the letter I. Okay. Here we're going to loop through that array, kind of like we did before, only now we're using an iterator. So we can say something like for it, iterator, equals names.begin, while it is not equal to names.end, it plus plus. See out? Okay, because it is an iterator, it's like a pointer. So actually, to see the data stored at any given location for names, we have to dereference it, and then we can print it out. Otherwise, we're just going to get a memory address. Let's set this as a startup and make sure we see our 3 names, and we do. So get used to this iterator syntax. You see it a lot in the wild. I know it might seem redundant because we can just for loop through this bad boy, but sometimes some of your collections, some of your containers may not support this natural sort of looping through them like our arrays do. So just get comfortable with this sort of iterator syntax. Take a minute, do this one again if you need to. Very important you're comfortable with this sort of syntax, in particular why we're dereferencing IT there. Okay, so another kind of thing we can do is defining an iterator using auto. So when declaring and initializing an iterator, auto can be used to simplify the declaration. So check this out. If we have an array of type int called int array, we can just say auto name of the iterator equals int array.begin. So that keeps us from having just to do this sort of syntax back here. Like, it seems redundant. It kind of is. You're saying the same thing, iterator. It's a lot of syntax, pretty wordy. So to get around that, you could just say auto aint equals int array.begin, and that will cause the compiler to basically determine the type of your iterator. Okay, let's take a peek at 1044 here. Yep. This is good. This is showing the same thing. So here's your array and your names. Here's your iterator. Okay, that's the same thing as creating an array of names. Then saying auto it equals names.begin. I'm not going to do this hands-on. We can just take a peek at it. It's basically saying the same thing as we saw up above. So here's your array of names. Then down here, we're actually saying auto IT equals names.begin. And yeah, we notice how we didn't like declare IT outside of the for loop. We did it right within the body of the for loop. Then we could say while IT is not equal to names.end, IT++, dereference IT, and we're going to see the same thing. So just a little shorthand syntax there. Okay, something called mutable iterators. And if you didn't know, mutable is a word that's thrown around in computer programming quite a bit. Mutable just means changeable. Is this thing changeable? Is it modifiable? If it is not mutable, you kind of say it's read-only. But if something is mutable, you say you can modify or change the thing. Okay, so mutable iterators. Iterators allowing modification of the array's contents. The iterators support pointer-like operations. If iter is an iterator, then saying star iter is the item it points to. In other words, we're dereferencing what iter is pointing to. You can also say iter++ to advance to the next item, and iter ---- to back up the container. Similarly, we can say end. That would point past the end. It should never be dereferenced. So that's an important point. End points to past the end of the collection. Because of that, you should never dereference it because you don't know what's going to be stored there. That is outside the bounds of the collection. Okay? Sort of like when we loop through an array, we always say size minus, well, we always say I is less than size. You could also say I is less than or equal to size minus 1. Things like this. That's why we never want to dereference end. Okay, traversing a container. We kind of did this already in some of the hands-ons, but we have our array. We have our auto iterator here equals a.begin. Then we can just say while iter is not equal to a.end, dereference whatever iter is pointing to. Then very importantly here, since this is a while loop, we have to say iter++ in the body of the loop. This isn't a for loop. We're not doing the auto incrementing sort of inside of the body of the loop or the condition of the loop. We have to say iter++ outside. And that's just going to happily loop through and print out all the elements of our array. Shifting gears a little bit to vector, and hopefully most of this will be a review. Similar to the array in that they're both sequential containers, but a vector does not have a fixed size. Elements are added and removed, and the vector adjusts as needed. And a vector has functions unique to its class, of course. Here's some examples of some constructors. So vector, then the type in your angle brackets, and the name of the vector. You can also say something like this: vector type ivect of size 20. So that's going to create a vector of size 20 ints. This is kind of the same thing, a size of 20, and then it's going to fill each slot of the vector with the data 0. And then here we're going to create a vector named ivec2 and initialize it with the values found in the vector ivec. This is a copy constructor and basically just does what it says. Copies the contents of a different array inside of a new array, and you're good to go. So some member functions. So you can say, give me the front, give me the back of the vector, give me the size, give me the capacity of the vector. Clear the vector out, clears or removes all the elements. We can push back, add an element as the last element. Pop back, you can remove the last element. You can insert a new one, add a location after that location or before that location. Very, very dynamic data structure. Page 1050. Okay, I think we'll just read through this one again since we've already done plenty of examples of vectors elsewhere. So here we have a size of 10. We're declaring a new vector of type int of size. So it's going to hold 10 int values. And here we're going to store the values 0 through 9. And we can just use square bracket notation to access and assign data to those particular slots of the vector. Then we can just print them out. And here, notice we're using the auto element in numbers. This is that very special shorthand for loop syntax. So what this is doing is creating an element iterator for each number in the numbers array. And then we're printing it out. And there's our result. Okay, storing class objects in a vector class object. So we don't just have to store ints or chars or doubles. A vector object can hold objects of a class as elements as well as primitive data types. So we can store strings, for example. When we do this, we then use the arrow operator with an iterator to refer to member functions of the elements. Inserting class objects in a vector, emplace and emplace back. So traditional ways to add an object to a vector include insert and pushback. Problem though is temporary objects are created taking time and using space. So there's better options in C++11 called emplace and emplace back. Pass the parameters for the constructor of the object to emplace or back. The function will pass the parameters as needed to the constructor. Let's check out 1052. All right. Yeah, I think we'll just read through this one as well. So we're defining our vector of size 5. We're defining an iterator pointing to the second element. So nothing wrong with doing this. We can say auto it, or iterator, equals numbers.begin. So that first element plus 1. So we're adding 1 to the it iterator to get us at the number 2, or a pointer to this element. Then we're going to insert a new element with a value of 99. So we can say numbers.insert. We're going to insert at the location of the iterator. That's important. We're not like specifying an index. We're specifying an iterator. So whatever this iterator is currently pointing to, that's where we're going to insert the number 99. Then we're going to use our little for loop shorthand and just print out everything in it. Very, very important to understand what this IT is doing. This is the current thing that IT is pointing to. If you did other stuff with IT above that, it would still be whatever it's currently pointing to. The current state of IT is where 99 will be inserted. Okay, space management. So we can insert number of elements that a vector can currently hold, get the size, get the max size. You can reserve. So if you know in advance that the vector is going to need more capacity, you can go ahead and make that optimization as you know that you're going to need it by calling reserve. And then you can, this is kind of cool, shrink to fit. If you've got a vector that maybe is much larger than needed, shrink to fit will reduce the capacity to be the same size as the size, freeing up unused space. So it's a way to kind of like clean up your vectors a little bit. 1053. All right, more vector examples here. So again, I think we'll just read through them. Feel free to pause the video and type along as you need. Again, a lot of this is going to be review except for the iterator stuff. So we're defining two vectors, type int. We're defining several iterators, so 3 of them in fact. So it1 is going to be the first vector beginning plus 1. So it's going to point at the value 2. The second iterator is just going to point at v2's beginning element, so 100. And then it3 is going to be v2.begin plus 3, so moving 3 spaces over. It's going to point at 400. Then we can insert a range of elements into v1, so we can insert v1.insert it1, it2, and it3. And then we can go through and simply print them out. In this case, we're printing out the elements of v1. (17.7), page 1055. Let's do this one. This one's a little bit larger of an example, so 17-7. We've got a little class action going on here, a little object-oriented programming. (17-7). Okay. Header file. All this is done in a single header file. What is this called? Product.h. Product.h. Okay, let's include string, standard namespace, class, product, private section, string, name, int units. Public section, here's our constructor for product, accepts a string called n and an int u. Name equals n, units equals u. Here's a setter, void, set name, string n, name equals n, void set units, an int u, units equals u. String get name, const, since we're not modifying anything in this method, we can make it const, return name, and an int get units, const, return units. Very good. Let's activate this project. Let's head back over to the main file here, and let's do this. Include IOStream, include vector, include product.h. Good. Now, we've created our own custom class just to prove to you that we can use that custom class in our vector. So we can have a vector of products, in other words. Vector products equals, and use a little syntax here to create some new products. Add a shirt, units 20. This is a product. Pants, I don't know, 10. Product, socks, 3. And then we can display them. For auto element in products, that's kind of how I would read that. I would say for, I need a semi there, yeah. For auto element, for auto element in products, do something, or each element represents an individual product, and then we can just say cout name element dot get name, and then units dot get units. And the biggest challenge here will be making sure that the product.h file is able to link correctly. Looks like it's fine. And we print them out. All right, moving right along here to the next one, I can see 17.8 shows an example of pushback to add a product to an existing vector, then using an iterator to display the contents of the vector. Notice the arrow notation. In those lines, it points to a product object. So arrow is used to call the objects get name and get units. Okay, let's just take a read-only view of this. So we've got 3 products, prod 1, 2, and 3. We have a vector of products, and then we're using, instead of initializing the vector with those products by default, we're using pushback to kind of one by one add each of the products to the vector. So pushback prod 1, prod 2, prod 3. Then we're going to create an iterator to display the vector's contents. So we have the auto keyword iterator equals products.begin, pointing to the first element. Do this loop while it is not equal to products.end, and then add 1 to the iterator each time. Now again, because it is a pointer, acting as a pointer, we have to use arrow notation. Back over here, we're saying the specific element. So we don't need to say arrow. We just say dot. Here, because again, it is a pointer, we have to dereference it and then call the getName method. So that shorthand, remember, is arrow, hyphen greater than, I guess. Dereferencing the pointer, calling a method is the use case for the arrow notation. Very good. That was 17.8, yes. So a couple more here, 17.9 and 10. Let's see what those have in store for us. Here's 17.9. Yeah, kind of the same. Let me back up one. So inserting elements with emplace and emplaceback. Some member functions like insert and pushback can cause temp objects to be created in memory when the insertion is taking place. For programs that do not make a lot of insertions, the overhead is not usually a problem. But if you're doing this a lot, if you're inserting a lot of objects into containers and removing them, insert and pushback can be inefficient. So to improve on this, we use something called emplacement to insert a new element. The process avoids the creation of a temporary object in memory while a new object is being inserted. As a result, emplacement functions are much more efficient, especially when a lot of objects are being inserted. And so that's basically your use case. If you know that you're going to be doing this a lot, use emplace and emplaceback. If you maybe don't care so much, and you're not doing it so much, you can just use the regular versions. Okay, same kind of program here. I won't rewrite it. It's basically just the same thing using emplaceback instead of pushback. Iterating through in the same way. Here's 10. So emplace. Member function constructs an object at a specific location. The first argument is an iterator. The new element will be constructed at that position just before the element that the iterator points to. After the iterator, you pass the list of arguments that are to be forwarded to the new object's container. Okay, so we've got a vector of products. We get the iterator. We emplace, so insert another product into the vector like this. So insert it at its location, IT's location. What are we inserting, etc. And then the whatever that is, the quantity, I guess. Cool. Okay, shifting gears here to maybe some data structures we're not as familiar with. Map, multi-map, and unordered map. So the map associative container stores two parts for each element. So each element has two parts. Sort of like an array which has an index and then the thing that's stored at the index. A map has a key, a unique entry associated with the element, and then the value, which is the data or the element associated with the key. Key value pairs are also called mappings, and each key is mapped to a value. Keys must be unique within a map. Otherwise, we don't know what the value is. If you have two keys of the same thing, you're not going to know what value to retrieve because it's ambiguous. So the map class is generic. The constructors require data types for the key and the value. The default constructor creates an empty map. The copy constructor creates a map and populates it with the contents of the map that is passed as a parameter. A map can be initialized via an initialization list, and each entry in the list must be a key value pair. I'm hoping we can finally see an example. Yes. Finally, so here's the map keyword, the map container, followed by the type of the key, and then the type of the data. So in this case, the student ID is the key, which is an int, and then the GPA associated with that student is a double. So the square bracket operator is overloaded. To assign a GPA to the student whose ID is that, you simply say this. So studata, don't think of this as an index. For every example we've seen so far, like with an array, we had square brackets, and then inside of the square brackets we had a number or an integer like this, but it meant index. That's not what we're doing here. 1 through 5 is the key value. It is not an index. It is a key value. So it's going to look up that key and store the value 3.25 at that location. Okay, I almost wish they wouldn't have used an int here. You can use any type for your key and your value. I almost would have preferred like a string here instead, just to really drive the point home. This is not an index. This is a key, and this is the value stored at that key. So the insert method adds a pair to the map. The pair must be created by makePair. So it looks like this. So if we want to insert a key value pair into student data, studentdata.insert, then makePair, followed by the key, followed by the value. So student ID 54321, the value of the GPA is 3.05. So the mPlace method will create an object and add them. So same kind of idea as with the vector. Studentdata.mPlace, student ID, comma, followed by the GPA or the value. So like sequential containers, maps can contain objects of a class. So they don't have to be primitive data types. Objects must be of classes that have a default constructor. Let's check out a hands-on on 1067. Yeah, this is the first time we've encountered a map, so let's go ahead and code this guy. Add project EX 1711. Include string, include map. Standard namespace. All right, let's create our first map. So map, the type of the key is going to be int. The type of the value is going to be string. We're going to call this map employees equals. Syntax can be a little funky for this. So this first set of curly braces represents the entire map, and then inner curly braces represent individual key value pairs that are stored in the map. So the ID of this employee is 101. The name is going to be Kevin Jones or whatever. And then we separate these with commas, so like this. ID 102, Bill Bob. ID 103, Jim Joe. And it looks like we got 4 here. 104. And that's our map. Okay, so we have key value pairs stored in this map. So now, if we were to access key 101, we would get back this name. If we were to access key 104, we would get back this name. Let's create an iterator for this. So map int string : iterator, and we'll call it iter, and see how we can access elements of this map. Now we can use the iterator to display each element of the map. For iter equals employees.begin, iter is not equal to employees.end, iter plus plus. Right? Yes. And we can see out ID, iter, dereference first. Now, that may not make total sense. Let's finish writing this. Then tab, name, iter, second. Let's make sure it works. Which example is 1711 right here? This is not a common way to use a map, by the way. You don't usually loop through maps in this way, but just to show you what first and second are kind of doing. Remember, these are key value pairs. There's 2 parts to each element of the map. There's the first part, and then there's the second part. So the first part in our case represents the ID. The second part represents the name. So when we say iter dereference arrow first, we're getting the ID. When we say second, we're getting the name. Okay. Next up, 1069. Storing vectors as values in a map, so you can do that too. Let's do a read-only version of this. It's pretty syntax heavy, but if you feel like pausing and typing it out yourself, please feel free. So here we have several vector of ints. So we have 4, student 1, 2, 3, and 4 scores. It is a vector of ints, each holding 3 scores. Now we're going to create a map to hold all the test scores. So check this out. So we have map. The key is a string. The value is a vector of ints. So now you start getting into nested angle brackets, which can scare people if you're not comfortable with such syntax. But just know, anytime you see an angle bracket, data type goes inside of that. A map storing string for keys and a vector of ints for value. Instead of just returning an int, we're going to return a vector of ints for the value of this map. So here we're going to do some assignments. So test scores at the key Kayla equals student 1 scores. Test scores for the key Lewis equals student 2 scores. Test scores at Sophie equals 3. Test scores at key Ethan equals student 4 scores. Then we're going to loop through and display each student's test scores. So element in test scores, display the student's name. We're going to say student, which is element.first, that's the name. And then we're going to have an inner for loop because our value is a vector of ints. So we're not just going to display one score, we're going to display all the scores. So we have to then say for int I equals 0, I is less than element.second, where second is the vector of ints size. And then we're going to print out, this by the way is a tab. So it's just a way of breaking up the text. So this is a tab. Print out the element second at location I, where again, second is the vector of ints. So the vector of ints at location I. Really chew on that if that makes sense. I congratulate you and we can go ahead and move on. 1071. What do we got here? Same kind of thing almost. Just a little bit of different way of expressing it. So create vectors to hold test scores. So here again, we have a map where the key is a string, the value is a vector of ints called test scores. We're going to go ahead and initialize that right away. So here our key is going to be the name Kayla. The value is going to be a new vector of int, and then here's your ints. Lewis, key, vector of int for your value. Sophie and Ethan, both again, vectors of ints. Then again, to display all that data, we're going to auto element in test scores. We're going to display element.first to get the key or the name. Then we're going to have to do an inner for loop to display each element in the vector of ints. So for auto score in element.second, print out score. Just using some different syntax basically to do the same thing that we saw in the previous example. Moving right along, so unordered map and multi-map. So unordered map, the keys are not sorted, has better performance for searching when the map is large. Multi-map, keys don't have to be unique. Duplicate keys are allowed. And then the equal range method supports iterating over all pairs that have the same key value. So it's like if you do have the same key, you have to have this special piece of code or syntax that will allow you to loop through all of those values that have the same keys. Then we can have count to determine how many pairs there are. Here's contact.h on page 1073. Let's check that out. Yeah, let's read through this. So basically, we have a contact with a name and an email. Got a constructor, getters, setters. Nothing super special there. Okay, here's our main method. So we've got a string search name, the name to search for. We're creating a bunch of contacts. Ashley Miller with the email, name, email. Create a map to hold the contact objects. So here we're going to have a map where the key is a string. The value is the contact object called contacts. Then we're going to have an iterator, basically the same type, called iter. Then we're going to add the contact objects to the map. So here's contacts, which again was our map. Contacts at this key. So contact1.getName, going to be Ashley Miller, equals contact1, the value. Okay, so this key equals this value. This key equals this value, etc. Then we can start searching, I suppose. Get the name to search for, so we're going to prompt for a name. We're going to get line the search name. Then we are going to use the find function off of our contacts. So contacts.find search name, and that's going to be assigned to the iter. Okay, so iter is going to point to whatever it found, whatever location it found when it ran its find function. So if iter is not equal to contacts.end, meaning it was able to find something, print out iter arrow second.getName and iter arrow second.getEmail. Because remember, second is the contact object. It's the contact object, so it can do getName, getEmail. Otherwise, contact not found. What else we got here? 1715. So again, we're referring to contact.h, so we're going to create some contact objects, create a map to hold them. Same kind of thing. I don't really see any difference in this example, so we'll move right along. 1076, 716. Okay, create a map to hold the contact object. So we've got a map. Key value is string. Value is a contact called contacts. So here we're defining the name. I don't like this at all because if you know anything about computer programming, you don't want to repeat yourself. DRY, don't repeat yourself. Dry. We're repeating ourselves here. We're saying the name twice. We're saying the name for the key in the map elements, and then we're saying the name when we create a new contact object. Not a very good example, if I may say so. We're repeating ourselves many times. We had 1,000 entries in this map. There'd be a lot of duplication. Then we're simply looping through and printing out the get name and get email. Bad example. Okay, let's check out customer.h. I think that there's nothing much special going on here. Again, a customer number, a name, got some constructors, getters, and setters. Looks like we're overloading the less than operator, where we're seeing if customer number is less than the other customer number. So when we say, is customer 1 less than customer 2, we're really comparing the customer numbers here. Just keep that in the back of your mind as we look through these hands-on examples. When we say less than, we're really referring to the customer numbers, which are integers. And as we know, integers support less than, greater than comparison. Okay, so I actually skipped over 17. Let's jump into 18. Right here. So we got customer.h included. And here we're going to create a map to hold the seat assignments, I suppose. We've got a map where the key now is customer and the value is a string. Called assignments, so the key is a new customer with an ID of 101 of name that, and then the seat assignment is the value 1A. So 1002, Austin Hill, 2B, and then 3C. Then we're going to display all the objects just like we're very much used to. 17. Whoa. There. Unordered multi-map class. So like unordered map, the keys are not sorted. Like multi-map, keys do not have to be unique. Page 1081. All right, so check this out. So 2 elements with the key Will, 2 elements with the key Faye, and 2 elements with the key Sarah. Shows how to define a multi-map and initialize them with these elements. So here, instead of just saying map, we're saying multi-map. Key is string, value is string. And again, just showing you that we can have now multiple keys with the same values. Alrighty, the set, multi-set, and the unordered set classes. Excuse me. So a set is a collection of unique values stored in ascending order. A multi-set, the values do not have to be unique. An unordered set is like a set, but there's no order. And an unordered multiset is like a multiset, but no order to the elements. 1082. All right. Get number of elements with specified key. So here we have a multi-map. Key is string, value is string called phone book. Guess what we're going to store in there. Key is name, value is phone number. Displays the number of elements that match Faye. So you can just say the name of your multi-map called phonebook.count and then pass in the key. That will tell you how many elements have that key. To retrieve elements with the specified key, you can do something like this. So here we have a multi-map defined just as we did before. Then we can define a pair variable to receive the object that is returned from equal range member function. Looks like this. So pair, multi-map, iterator, multi-map, key, value, iterator called range. Then we define the iterator for the multi-map, like so. Then we can get the range of elements that match Faye. So you can say range equals phonebook.equalRange Faye and then display them all. They'll then be stored inside of this new multi-map. Okay, let's shift gears from the various data structures or containers and talk a little bit about the algorithms involved in the STL. So it contains algorithms that are implemented as function templates to perform operations on containers. We have to include the algorithm header file. Some of the algorithms included are binary search, count, for each, find, max element, min element, random shuffle, and sort. That's a fun one, sort. You just say elements.sort and you'll get back a sorted collection. Many STL elements manipulate portions of the STL containers specified by begin and an end iterator. So it's good we know what we know now about iterators because the algorithms rely on them. For example, if we called the sort function, we need to pass in two iterators because we'd be sorting the elements between the first one and the second one, ascending order. You can certainly say iter 1 is the beginning and iter 2 is the end, and you be able to sort everything in between. But you don't have to. You can just sort a portion of the collection of whatever you're looking at. You can do a binary search. So again, you'd pass in two iterators, the range basically that you want to search for, and then of course the value that you're actually looking for. Page 1094. Believe this is an example of binary search. So notice how we included vector, we included algorithm, and we have a value that we're searching for. We have a vector of numbers. We're going to sort the vector first. So we can just say sort, and remember the two iterators, we're going to sort from begin to end, and that sorts it sort of in place. It's not like I'm reassigning numbers. I'm basically sorting them in place, or the STL is doing it for me. Then I'm going to print them out, and then I can say, give me a value to search for, and here's my call to binary search. So binary underscore search, starting at the beginning, ending at the end, searching for the search value, and we've included this in an if statement. So if the result of this is true, then print out that it's found. Otherwise, if it's false, it was not found. 1096. So here we're working with our customer header file. So again, we've got a search value, an integer. We've got a vector of customers. We are going to sort the vector, beginning at the beginning and ending at the end. Remember, sorting by customer number. So by that first integer there, I'm going to print out the sorted customers and then get the customer number to search for. So we can binary search from the beginning of the customer's vector to the end. And we're searching for search value, like you see here. And if it returns true, yes, it was found. Otherwise, no, it was not. All right, let's check out this kind of one-off examples. So this STL's isPermutation function determines whether one range of elements is a permutation of another range. And it wants 3 iterators, so isPermutation accepts iterator 1, 2, and 3. So iterator 1 and 2 mark the beginning and the end of the first range of elements. Iterator 3 marks the beginning of the second range of elements, assumed to have the same number of elements as the first range. Returns true if the second range is a permutation of the first, returns false otherwise. Here's kind of what it looks like. Got 2 vectors. We've got a winning numbers vector. We've got a player vector. We're going to get the winning numbers. Looks like we're getting those from the user. Getting numbers purchased on a lottery ticket. So enter your lottery numbers. Okay, this is on the ticket. Check for a winner. If the numbers that the player has entered are included in the winning numbers, that's a win. Otherwise, it's a loss. All right, function pointers. So executable code for a function can be accessed via a function pointer. Like an array, the name of the function serves as its address. The STL is functions that can pass container elements to functions like for each and COUNTIF. 1100. All right. Yeah, for each function. Okay. So here we got a function prototype called double number. Nothing much going on in there other than taking the number passed in, multiplying it by 2. We got a vector of numbers. We're going to display them before doubling. Then we're going to say for each numbers.begin, numbers.end. So this should be comfortable for us. So this is going to say the beginning of the numbers vector and to the end of the numbers vector. And then we're going to use this double number function on each element inside of that range. That's kind of cool. That's calling double number from the beginning of the array to the end of the array on each individual element. When we do this, this is called a function pointer. We're simply passing in the name of the function that we've defined down here and using it in our for each. Pretty neat. No special syntax at all, just saying the name of the function. So set operations on containers. So the STL includes functions to perform set operations like union, intersection, difference, symmetric difference, and inclusion. If those terms don't make sense to you, that's fine. They're outside of the scope of this class. They're discussed a lot in a class called discrete mathematics, where you talk a lot about set operations. They take iterators as parameters that mark the beginning and the end of the ranges to use for each set and for the location to store the results. Function returns true or false to indicate if all the elements are inside of the set. I'm not going to spend a lot of time on these different set operations. Again, they're really for a different kind of class, more of a math class. But if you want to look at the union, the definition of the union between two sets is a set that contains all the elements of both sets with no duplicates. So an example, set 1 is 1, 2, 3, 4. Set 2 is 3, 4, 5, 6. The union is 1, 2, 3, 4, 5, 6. And you can tell the STL to do this. You can say set union to give you back the union of the two sets, stores the union in a third container. So that kind of looks like this. We've got a set 1, a set 2. We've got a vector of results. Create a vector to hold the union. The vector must be large enough to hold both sets. I guess that's important. So we're adding set1.size plus set2.size. That's the size of the result vector. And now to actually get the union, we can say set union starting at set1's beginning, set1's end, the second set, set2 beginning, set2 end, and then store the result in result.begin. Then we'll resize the result vector to remove excess space like this, and then show them. And that will get you the union of a set, should you ever need it. I'm going to skip over the intersection. Basically, an intersection is intersection of two sets. So basically, only the elements found in both sets. So here's an example, 1 through 4. 3, 5, 6. The intersection is going to be the numbers 3 and 4. Again, concepts better suited for a different class. Lambda expressions, though, are pretty cool. So the function operator open close paren can be overloaded. An object of a class that overloads the function operator is a function object or a functor, new key term. Here's an example. So function object example, class that overloads open close paren. And it looks like this. So we've got a class called multiply. We've got our public section. We've got keyword operator. Remember, that's how we kind of override or overload default behavior of built-in C++ operators. In this case, we're going to overload the open close paren. We're going to say, to do that, we're going to pass in an int called x and an int called y, and return the resulting multiplication. Create and use the objects. So here we can say, create me a new multiply object called prod, and then create an int called product, which is going to be equal to prod passing in 4 and 3. Now when we do that, when we pass in 4 and 3, sort of automatically it's going to jump over here and return the product of those two integers. You can create and use in the same steps. You can do something like this if that suits you better. You don't have to do two separate steps. You can combine it into one line. The object created in the previous example is called anonymous. That's actually kind of important. Up here, our multiply object was called prod. Down here, it's called nothing. We have the product, which is the result calculation, but there's no multiply object name here. We're just anonymously calling it. All right, 1733 is going to make our way through here. And yeah. So here we've got a sum object, and all it's doing is overloading the open close paren, passing in two integers, returning their sum. So here we include it. We've got some local variables, x, y, and z, 10, 2, and 0. We're going to create a sum object like this. We're going to call the sum function object. So z equals sum, passing in our x and our y, displaying the result. And because we overloaded that in the class definition, we know that that's just going to return the result of x plus y. Here's isEven, classic isEven function. All we're doing is overloading the open close paren, passing in a single integer now, and returning whether or not that integer modulus number 2 is equal to 0. If it is, that means that we have an even number. We can use it here. Read through that. Use there. Cool, making good time here. Uh, 1735. Yes, so here we're using isEven again. Kind of the same thing. All right. Kind of the last big idea of the chapter. So predicates. So a predicate is a function that returns a Boolean value. Function objects can be created to perform tasks associated with predicates. You can have a unary predicate, which takes one argument parameter, and a binary predicate, which takes two. Here are some examples. Unary predicate. So a predicate takes a single argument. This would be like the isEven code that we just looked at. So something like isPositive. We're overloading the open close paren, we're returning a bool, and we're just passing in a single integer. This is a unary predicate, and we're returning whether or not that integer is greater than 0. Here's a binary, greater than, so it takes two arguments, again overloading the parens, taking in two arguments, returning whether or not x is greater than y. Lambda expressions provide a simplified way to create a function object. So here's some examples. So in a multiply example, we can say open close square bracket, passing in two ints, return x times y. There's no there's no name of the function here. This is kind of an anonymous function call. Similarly, for isPositive, we can say pass in an int, return whether or not the int is greater than 0. It's like a sort of an inline way of defining a function quickly without having to deal with all the formalities of like prototyping it and giving it a name and things like this. You can, though, give it a name. You could say something like auto is positive, looks something like this. Square bracket auto x, return whether or not x is greater than 0. This is pretty nasty syntax, if I may say. So we say that the square brackets are the lambda introducer, where the lambda expression begins, and the square brackets may include a capture list of variables in the surrounding scope of the expression that can be used in the function body. No surprises there. You can capture some parameters and use them. Parenthesized list following square brackets is the parameter list, and those are used by the operator open close paren function. And of course, the code in the curly brace is the function body. Almost done here, 116. This stuff, by the way, lambda expressions, gets into a larger discussion of something called the lambda calculus, which they teach at universities. There's like entire classes or sections of courses on how to do lambda calculus. It's really not as painful and difficult as it may sound. Lambda calculus is just a way of like formally defining your functions and how they call each other. But anyway, here's 1736. What are we doing here? Oh, good, a lambda expression. Okay, we've got a vector of ints. We're going to use a lambda to create a function object called isEven. Here's the beginning of the lambda followed by the parameter list. We're going to return whether or not that is even, whether or not the modulus of the x is equal to 0. And we're going to get the number of elements that are even. So COUNTIF, starting with v.beginning, ending with v.end, and using this lambda expression called isEven, and then just showing how many even numbers we have. Kind of a very elegant way of doing this. Notice how there's no like for loop here. We're dealing with a collection of data, a collection of integers, but we're never actually iterating over it. We're just using these built-in ideas in C++, like lambdas and COUNTIF, to kind of do all that looping for us. Finally, functional classes. So require the functional header file. Here are some examples, like less returns true if a is less than b, less than or equal, greater than equal. Notice the t. That harkens back to our lesson on templates. That's very much what we're doing here. In order to use a data type in those angle brackets, the t must support whatever operation is listed over here. So the t must support less than or equal to, greater than or equal to. So function objects can be passed as parameters to functions. So for example, sort, you can sort an array or a vector. The function parameter is used to determine how to compare the two values. And removeIf can remove elements from an array or vector that meet a criteria. Function parameter is used to define that criteria. I'd also say that if function pointers passing function objects to functions, you need a good concrete example of this. Game design comes to mind. When you're working in your C++ code and your game engine and you're defining like your input mappings, one way we would use this is to say like, okay, the player presses the spacebar key. What function am I going to run when the player presses the spacebar key or the E key or any kind of input? Some function in your code needs to run when the player presses that input. And how we specify that is simply saying, here's a pointer to the function that I want to run when a player does X, Y, or Z. And it's that easy in the engine code. Finally, 1117. Here's I believe this is an example of a sort. Yeah. Takes a comparison function as an optional third argument. The third argument can be a function pointer or a function object. Here's an example. So we've got a vector of ints. We're going to display them. We're going to sort them starting at the beginning, ending at the end. Show them again. Now sort the vector in descending order, beginning with the beginning, ending with the end, and using this guy. Yeah, comparison. This is your comparison function in this case. And then displaying it again in descending order. So that's sort of interesting. It shows the nuance of everything that comes up in C++, it's like, okay, I want to say that I want to sort this vector of integers. So I could call sort on it. But does that mean that I'm going to be sorting ascending or descending? Well, C++ gives you the power to specify which. And then there is a default behavior. You can see here the default behavior is sorting ascending. But if you want to sort descending, you can pass a modifier to the sort function that will allow you to do that. So ends chapter 17. Again, kind of a whirlwind tour of the standard template library. Concepts that really exist, they transcend all programming languages. Most languages have some idea of this in them. They don't call it the STL, but they all support things like vectors, lists, stacks, queues, etc. So in the coming chapters, we're going to talk about some more of these data types specifically, like stacks, queues, and lists, and see what kind of operations they allow us to perform. And we also get to talk about what good are they? Why would we want to use a stack over a vector, for example? Those kinds of questions make great interview questions, by the way. So more on that coming up. For now, I'll say thank you very much. Hope you enjoyed chapter 17.